Welcome people! Today we're going to apply Laplace transform on two functions. In the previous video I talked about the Laplace transform and gave some intuition and about the formula, why this formula, what does it mean and why do we use this formula, by giving some examples from power series. You can go and watch that video before watching this video if you don't know what Laplace transform is. Today we're going to apply Laplace transform on two functions. First one of them is 1. We're going to apply Laplace transform on 1. So f of t is 1 here, it's a constant function. This is equal to the integral from 0 to infinity of, so this is just 1, this is the integral of e to the minus st dt. If I integrate this, I get e to the minus st divided by minus s, because this is the s, we are treating s as a constant because we're integrating over t. S for now is just a constant. And this expression evaluated at 0 and infinity. And there's an important point. We're assuming that s is greater than 0. So s must be a positive number. When t goes to infinity, this is equal to 0 because it's going to be e to the minus infinity, which is 0 at the limiting point of infinity. So this is equal to 0 minus, if I put 0, I get e to the 0 divided by minus s, which is 1 over minus s. So minus 1 over s, as you can say. Minus minus makes a plus. So this is equal to, right here, 1 over s. So the Laplace transform of 1 is equal to 1 over s. Be careful. This was a function of t. Even though it was a constant function, it was a function of t. And we got out a function of s. This is why we call it transform. It transforms our function into a different variable. So let's do the Laplace transform for different function now. Now we're going to apply Laplace transform on e to the at. This a is just a constant number, don't worry about it. It doesn't have to do anything with the power series a. Fine. So this is equal to integral of e to the at times e to the minus st from 0 to infinity. If you wish to, you can evaluate this integral, you can integrate this function, but I'm not going to, because there's a much easier way. So I'm going to write this integral, I write the expression inside this integral. So this is e to the at times e to the minus st. If I combine the exponents, I get e to the at minus st. Okay. So what I'm going to do is that I'm going to factor out the t here. So this is equal to e to the t times a minus s. And I'm going to factor out a minus 1 from this. So I'm going to just multiply it by minus 1. And I get minus, so the signs flip, and I get s minus a times t. That's e to the minus s minus a times t. Let's rewrite the integral as from 0 to infinity of e to the e to the minus s minus a times t et. Why did I do this? Not to integrate it easier. If you look at the Laplace transform of 1, it is just, think that you put in 1 into f of t here. When you put in 1, you get e to the minus st. And here you get e to the minus s minus at. So you can think of this s minus e as this s. And when this was s, the Laplace transform was 1 over s. Now we have minus s minus a times t instead of minus st. When it was minus st, it was 1 over s. So in this case, we can say that this is equal to 1 over s minus a. Because we have, so just think of any other variable. So say that this is e to the minus omega, this is not omega, this is w, omega t, in the, think of this as the expression in the integral. When this was equal to s, it was 1 over s. If this is equal to s minus t, then this is equal to 1 over, so s minus a. So when this is equal to s minus a, then the integral is equal to s minus a. That's why the Laplace transform of e to the at is equal to 1 over s minus a. Thanks for watching. In the next video, we're going to apply the Laplace transform on sine and cosine functions.